All right, open up your book to section 6-3. We're on page 295 in your book, and the title of this section is the graphs of tangent, cotangent, secant, and cosecant functions. We've already looked at the graphs of sine and cosine, and looked at the general sinusoidal equation from those functions as well. And now we want to look at what the other four functions look like. So the objective there is to plot the graphs of tangent, cotangent, secant, and cosecant functions, showing the behavior when the function value is undefined. Now, of course, you could just grab your calculator, punch those in, and see what the sketch looks like. But I guess the bigger question is, why do you end up with the sketch that you end up with? And so that's what we're going to take a look at here in this section. All right, so there's a couple of properties that we need to talk about. Two of these here are properties we've already seen and talked about. That's the reciprocal properties. If you recall, the reciprocal properties tell you the definitions of those three new trig functions we learned in the last chapter. That is, we probably walked in knowing SOHCAHTOA, sine, cosine, and tangent. The three new ones for us were cosecant, secant, and cotangent. And we learned that those three functions there turn out to be just the reciprocals of the three functions we already know. And in fact, that's how we calculate those with our calculators. We just simply find the reciprocal of the quantity that we're looking for to be able to evaluate cosecant, secant, and cotangent. We don't have those buttons on our calculator. So secant we learned was equal to 1 over cosine of theta, and cosecant we learned was equal to 1 over the sine of theta. Those are the reciprocals. There's a third property here, but I'm just going to worry about these two, since those are the two we're going to deal with. And then the other two properties that I want to talk about are the quotient properties for tangent and cotangent. You'll notice that with all four of these properties here, we're going to be able to write these four trig functions in terms of just sine and cosine, which is going to be nice because I know what the graphs of sine and cosine look like. I can use those to help me understand what the graphs of these other four trig functions are going to look like. So your quotient property is there for tangent. Tangent is equal to the sine of theta divided by the cosine of theta. And cotangent of theta is defined as the cosine of theta over the sine of theta. Now, we previously had talked about the fact that cotangent is the reciprocal of tangent. So if we know that tangent, sine over cosine, reciprocating that gives us that cotangent property there. So we shouldn't be surprised by that part right there. But let's make sure that we understand why this is the case here for the quotient properties. And we'll do that with a little proof. So let's take a look at a point here. We'll call it UV. I've sketched it in the first quadrant, but it doesn't have to be in the first quadrant. It could be anywhere. Point UV, and I've marked that as a point on a terminal side of some angle theta. And we've measured the distance there from the origin to that point and called it R. So we've got our UV and R, in other words, from this. All right, so let's just write down what we know about sine and cosine based on our definitions from the last chapter. We said that the sine of theta is equal to V over R. The cosine of theta is equal to U over R. And so now let's see what happens when we take the ratio, or the quotient there, of the sine of theta over the cosine of theta. I take sine of theta and I divide it by the cosine of theta. We're claiming that this is going to give us tangent. Let's see if that's what we end up with. So sine is V over R, and cosine is U over R. Of course, if I'm dividing these two fractions, I can rewrite this as a product. So I can write this as V over R times R over U. Remember, you got to reciprocate that denominator in order to change it to multiplication. And of course, when we do that, that turns out to be nice because the R's will cancel each other out. And you're going to be left with V over U. Oh, that turns out to be pretty nice because we defined tangent of theta as being V over U. So this is equal to tangent of theta. There we go. That's actually our little proof there that sine of theta over cosine of theta does in fact turn out to be the tangent of theta. You could go through the same process there to show the same is true for cotangent, or you can use the definition of cotangent, that it's the reciprocal of tangent, to get that second property there. All right, so we're going to use these reciprocal and quotient properties to help us sketch the graphs of tangent and cotangent, secant and cosecant. Again, the key is that we're rewriting these in terms of two functions, sine and cosine, that we already know the graphs of those. And then using those graphs, I should be able to come up with what the sketch of these other four must look like. All right, so take a look at example 1 there on page 296. We're going to actually come up with the sketch of two of these. And then once you see how to do it for these two, that'll help you see how you do it for the other two. But let's take a look at the sketch of cosecant of theta, is what they want you to do for example number 1. Sketch the graph of cosecant of theta. Well, cosecant, the reciprocal property for cosecant is it's 1 over sine. So we're going to use the graph of our sine function to do this. So let's start out by doing that. I've already got it sketched here, but you can do the same thing on your paper. Give yourself some space like I've got here in my sketch. So you can see I've got actually, what, 1, 2, well, a little more than 2 periods of this thing sketched here, but roughly 2 periods is fine. And it oscillates between 1 and -1 there. And it repeats every 360 degrees, crosses through the origin, increasing as it crosses the sinusoidal axis there. All right, so that's our graph of what the sine function looks like. That's what we got to start with. Because of the fact that I'm trying to sketch cosecant, which is the reciprocal of this thing, that's why I'm starting with this function here. We're going to keep coming back to this sketch here. Well, let's go through the steps that you should kind of think about as you are trying to sketch this thing. So the next thing to consider are the vertical asymptotes, or the first thing to consider are the vertical asymptotes. Since we're sketching 1 divided by the sine of theta, that means anywhere that the sine of theta is 0, we're going to be undefined. We'll be dividing by 0. We learned when we studied rational functions or rational algebraic functions, those are going to be vertical asymptotes or removable discontinuities. In this case, since there's no common factor with the numerator, it's going to be an asymptote that we run into. So if sine of theta is equal to 0, that means that 1 over sine of theta is going to be undefined, because you're going to be dividing by 0. So those are going to be vertical asymptotes for us. So on our sketch up here, I'm just going to mark the vertical asymptotes. I'll do this in blue here. So anywhere that I see the sine function hits the x-axis, I'm going to mark that with a vertical dotted line here. So I can see that I'm crossing right through the origin. So right on our y-axis, we have a vertical asymptote. At 180 degrees, sine hits the x-axis again. I've got myself a vertical asymptote. 360, same story. 540 again. And then finally 720. And obviously it would continue doing that. It looks like every 180 degrees, the sine function hits the x-axis, so we'd have a vertical asymptote. All right, the next thing we're going to consider are the zeros of this function. And the zeros of this function would be where our reciprocal of sine would be equal to 0. Now in this case, turns out there are none, but in some cases there might be, when we look at their graphs, we might have some x-intercepts. But if you take 1 over sine of theta and try to find out where that's equal to 0, you're going to find there's no solution to that. When you have a rational expression like that, you multiply both sides by that denominator and try to solve, you'd end up with 1 is equal to 0. There's no solution to that. So there's no x-intercepts. In other words, we're never going to cross the horizontal axis here. Okay? Unlike the sine function where it crosses it an infinite number of times, we're never going to cross it. So we have vertical asymptotes here, but I know that I'm not crossing the x-axis in between those. Now the reason I listed those, by the way, is because when we look at the next example, we'll still go through all of these same steps. And you'll see that sometimes you have x-intercepts, sometimes you don't. All right, the fourth thing to do is to look at some key points. And the key points that we're going to consider here is thinking about the sine of theta equaling its upper bound or lower bound. The upper bound of sine is 1. The lower bound is a negative 1. That's the highest and lowest y values that it takes on. That's the endpoints of its range. So if the sine function is equal to the highest point or the lowest point, then that means that 1 over sine, that's cosecant, that's what we're trying to sketch, is equal to the reciprocal of plus or minus 1, which is just plus or minus 1. It's the exact same thing. So in other words, anywhere that sine hits its high point, that's a point that it shares with this sketch. And anywhere that the sine function hits its low point of negative 1, the reciprocal of a negative 1 is still a negative 1. So it's going to hit that point, and it's going to hit this point, and it's going to hit this point, and so forth. Those are the points that my sine function and cosecant function have in common. In fact, it turns out those are the only points. Next thing to consider here is the behavior near your vertical asymptotes. And we talked about doing this with rational algebraic functions, that sometimes we got to be a little bit more careful near our horizontal or vertical asymptotes to figure out, am I above or below this horizontal asymptote, or what's happening to the left and right of this vertical asymptotes. That's what we're going to look at here. We're going to look at the vertical asymptotes. If the sine of theta is close to 0, so when sine is getting really, really close to 0, and it's positive, it's greater than 0, then when I consider the cosecant function, cosecant again is 1 over sine, and that means 1 over sine is headed toward positive infinity. And the reason for that is because you're taking the reciprocal of a really, really small number. If you're close to 0, we're talking about really small numbers, 0.1, 0.01, 0.001. So if I take the reciprocal of a really, really small number, I end up with a really big number. So it's going to positive infinity. So on my sketch up above here, I'm going to come back to this in a second here, but on my sketch, what that's saying is, I can see that my sine function, for example, right here is headed towards 0, and it's getting really, really small. They're just barely above the x-axis, but they're positive. Same thing is happening over here. But as I head towards that value of 180 degrees, the sine is getting really, really small, the sine of those values. So when I reciprocate those, I end up with large values. So when I go to sketch what this looks like, I would expect that I'm headed towards positive infinity over here on the left side. And again, the same thing happens over on the right side. Let's look at the next place that we see that happening. Here I see that my sine function is headed towards 0 and they're positive values. Here over here on the right, they're headed towards 0 and they're positive values. So the reciprocal of those really small positive numbers are really big positive numbers. So I'd expect that my graph is starting at positive infinity and ends heading towards positive infinity in that little interval. All right, let's talk about what happens in the other half of this. So if the sine function is close to 0, so again, we're talking about getting values really close to 0, but they're negative. So now instead of being 0.1, we're talking about a negative 0.1. Our sine function is going to be below the x-axis when we look at the sketch. Negative 0.1, negative 0.01, negative 0.001, and so forth. If you reciprocate that, take 1 over that sine value, you end up with a really big negative number. So that's why it's headed towards negative infinity near those vertical asymptotes. All right, so let's take a look at our sketch up here then. And again, we'll mark a few key values that we see here. So here I can see that as I head towards this vertical asymptote there, sine function is below the x-axis. Those are really small negative numbers. They're getting close to 0, but they're slightly negative. Same thing is happening over here on this side, that they are really small negative numbers. Maybe I should do that in a different color here for us, so I don't have green on both sides. Do that in purple. Okay. So what does that tell me? Well, when I reciprocate those really, really small negative numbers, I get a really big negative number. So I'm headed towards negative infinity over here, and then I'm headed towards negative infinity over on the other side. Same story here on this interval. These are really, really small negative numbers there. These are really, really small negative numbers as I head towards that vertical asymptote. So when I reciprocate those, I end up with really big negative numbers. That's negative infinity that we're headed towards. Negative infinity on that side. So there's the sketch in red of what the cosecant function looks like. Cosecant looks like this graph right here. It has a bunch of kind of U-shaped sections to it. Those are separated by vertical asymptotes there, so they're not parabolic. Or a parabola or a quadratic function does not have vertical asymptotes there. So it does look like that U shape that we might expect with a quadratic, but since there's vertical asymptotes, it's not going to be quadratic in there. All right, that's the graph of cosecant. All right, take a look at example number 2. Example number 2 is going to ask us to do pretty much the same thing here, but they're going to ask us to do that for a different function. It says on paper, sketch the graphs of sine and cosine. Use the quotient property to sketch cotangent. So we're going to sketch cotangent. By the way, we just sketched cosecant. If you want to graph secant, you'd go through the exact same process. You're going to use the reciprocal property, but you'd start out with cosine of theta and go through those exact same steps. All right, so let's start out with sine and cosine. Graph starts out a little bit more confusing here because of the fact that I've got to have both sine and cosine sketched here. So keep track of which one is which. Sine is the one that goes through the origin. Perhaps I should have sketched these in different colors there, but sine is the one that goes through the origin. Cosine is the one that starts out at x equals 0 is at its high point of 1. So those are our two graphs there, sine and cosine. We're going to use those two to come up with the sketch of cotangent. And cotangent is cosine over sine. All right, now the good news is since we're dividing by sine here, the example we just did, we are dividing by sine. So many of the properties we found when we were dividing by sine with the first example are going to apply right to this same thing here. All right, let's start out with the vertical asymptotes as the place to begin. Find out where this thing's undefined, in other words, is what we're starting with. Your vertical asymptotes are going to occur where the denominator is 0. Since we're dividing by sine of theta, if sine of theta is 0, we're dividing by 0, so we're going to be undefined. So anywhere that you have the sine function hitting the x-axis, we got ourselves a vertical asymptote. So sine goes right through the origin, so that means at 0, we got a vertical asymptote. At 180, we got a vertical asymptote. Again, notice that these vertical asymptotes occur in the exact same places that we just had with the graph of cosecant. That's nice. 540 again, and then 720, and obviously these would continue on in both directions there. You'd have an infinite number of vertical asymptotes. All right, the next part, or the next step, is to look at the zeros. Now, in the previous example, we didn't have any zeros. But in this one here, we're going to have some zeros. If you think about taking the cosine of theta and dividing it by sine of theta and setting that equal to 0, you can solve that rational expression there by multiplying both sides by that denominator. And of course, you'll end up with a cosine of theta equals 0. So anywhere the numerator is 0, in other words, that's where the zeros are going to show up. So let's go ahead and mark those. Anywhere that the cosine function is equal to 0 or crosses the x-axis, the cotangent function is going to do the same thing. So it looks like at 90 degrees is the first one we see there, that we are hitting the x-axis. That's halfway in between those vertical asymptotes. 270, it looks like we have the same story. Well, that turns out to be pretty nice. Again, that's halfway in the middle there. And again, at 450, that's halfway between our vertical asymptotes, 630, and it looks like that would continue. It looks like we're going to have x-intercepts right in the middle of each of these subintervals here that we've divided up by these vertical asymptotes. All right, the next thing to consider are some key points here to plot. If there's some key points that you can sketch, then go ahead and sketch that. That might help you come up with the right graph of this. So let's do that. If sine of theta is equal to plus or minus cosine of theta, we'll deal with the plus first, and then we'll deal with the opposite in a second. But If sine of theta and cosine of theta are equal to each other, that means they're actually intersecting. Then when you calculate cosine divided by sine, that's cotangent, cosine over sine. Since they're equal to each other, the numerator and denominator, we must end up with 1. So let's find everywhere that the two functions intersect. And since they're equal at that point, we'll plot a point at y equals 1. Not at the intersection, but at y equals 1 is what we're going to sketch. We'll come back to this and deal with the opposite here in a second. All right, so I can see that the two functions, I'm going to mark this in a different color here, but I can see the two functions intersect right here. Since they intersect right there, that means I can plot a point at y equals 1 right at that same x value. So right there is my point that I'm plotting. I can see that those two functions intersect right here again. So that means that their values are exactly the same. If I take two of the same numbers, and divide them by each other, I get a value of 1. So I'm going to plot a point up here at y equals 1. Again, it's not the intersection that I'm plotting. I'm using the intersection to figure out where do I plot this point. Find another intersection right here, because that means that the two functions are equal to each other, and I plot a point up here at y equals 1. And it looks like there's one more here to mark. This right here is another intersection. So I'll plot a point up here at y equals 1. All right, the ones that are not as easy to find are the ones where they're opposite. If I go back down here again, it says that if sine is equal to plus or minus cosine of theta. We did the plus. So when sine is the opposite of cosine, so that means if I look at the sine function, if it's above the x-axis and the cosine is below the x-axis by the same amount, they're just opposites of each other. One's above and one's below. That means that when you take the ratio of cosine over sine, since they're opposites of each other, that means you're going to get a -1. So instead of plotting a point up at y equals 1, we're going to plot a point at y equals -1. Again, the intersections are really easy to plot here, and sometimes you might even sketch a negative cosine of x along in this graph here to help you find these ones. We have just cosine and sine, but if you sketch negative cosine in here, it would help you out, because you'd be looking for the right intersection. But I think we can do this even without that. If you measure, for example, looks like about right here, if I measure that distance right there from the x-axis to that curve, that's my sine curve, and I measure that distance below to the cosine curve, it looks like those distances are the same. It's just that one's positive and the other one's negative. So if that in fact is the case, then that means the ratio at that point is going to be a -1. So I'm going to plot a y value at -1. And let's keep doing that. It looks like somewhere about right here that the cosine function now is above the x-axis. The sine function is that same distance below the x-axis. So the ratio of those two is going to be a -1. So I'll plot that point right here. Let's keep going with this. It looks like about right here that my my sine function is above the x-axis. My cosine function is below the x-axis by the same amount. So that means their ratios is a -1. By the way, you'll notice, by the way, these are showing up in the same spot in each one of these intervals. It's to the right of the x-intercept, but halfway between it and the vertical asymptote is what I'm using to help myself find them. And then finally at the end here, it looks like somewhere about right here that I've got these two functions with the exact same distance above and below the x-axis. They're just opposites of each other, so therefore their ratio would be a -1. So there's another point to plot. Again, the red points that I've got sketched there are actually points that my cotangent function is going to go through. The other marks are just helping me come up with those points to plot. All right, let's talk about the behavior around your vertical asymptotes. This is similar to what we just did there for the previous one. But if the sine of theta is close to 0, again, that's the denominator of this, and that means that the cosine of theta over the sine of theta will be headed towards infinity. And again, that's because you're taking some number divided by a really, really small number, 0.001, 0.0001, and so forth. You can determine whether or not you're headed towards positive or negative infinity by considering the signs of both sine of theta and cosine of theta. So this is a little bit different than what we said on the last one there, but I'm still considering what's happening around my vertical asymptotes. The key here is that I have to consider whether the numerator is positive and the denominator is positive. And if I take the ratio of two positive numbers, I, of course, end up with a positive result. When they have opposite signs, I'm going to be heading towards negative infinity. So it's the same signs, both positive, both negative, the ratio is positive. If they have opposite signs, then the ratio is negative. So let's take a look at what's happening here on our graph. Do this in a different color here. So if I look at what's happening around this first zero here that I see here on sine. Sine is headed towards 0 here, but it's a positive number because it's above the x-axis. The cosine function is up here. It's headed towards this value here, and of course it's positive as well because it's above the x-axis. So you have a ratio of a positive number, cosine, divided by a really, really small positive number, sine. So a positive divided by a positive is going to give me a positive result. So I would expect that this thing is starting up here at positive infinity, headed down towards something like this. Now the fact that I have that couple of key values sketched in here probably should help me figure out what direction this has to head as I approach my vertical asymptotes, but sometimes considering the behavior on each side helps you verify that. Now look what's happening here on the right side of this interval here, that is near the other vertical asymptote. My sine function again is headed towards 0, but it's above the x-axis, so that's positive. My cosine function is headed in this direction here. It's actually headed towards a value of 1, but it's below the x-axis. It's actually approaching a negative 1, so this is negative here. So now my ratio would be a negative cosine, that's a negative number, divided by a positive value for sine, so a negative over a positive is a negative number. I'm going to expect to see that this is headed towards negative infinity now, and that's why it heads down in this direction. All right, and you can do that same analysis on each of these intervals here. We'll do the next one, and then we'll just continue on with it from there. But I can see that my sine function, again, is headed towards 0 right here, and it's below the x-axis, so that means it's negative there. My cosine function is right here. It's headed towards a negative 1, which means it's negative. So I've got a negative for my cosine value divided by a negative for my sine value. Negative divided by negative is a positive number, so that's why this is going to start out up here at positive infinity and go through those points. And on the other side of this, here's my sine function. It's headed back towards a 0, but it's below the x-axis, so it's negative there. Here's my cosine function, the numerator of this. It's above the x-axis, so it's positive here. It's positive, getting close to positive 1. So again, you've got cosine, which is positive, divided by sine, which is negative. A positive divided by a negative, that gives me a negative result. This is going to head towards negative infinity. Now you can continue doing the same analysis over and over again here, but you'll see that you end up with a graph that kind of does something like this. And you'll notice that this repeats every 180 degrees. It doesn't take 360 degrees like you see for sine and cosine, or secant and cosecant, but rather cotangent and tangent repeat every 180 degrees. I get the exact same graph every 180 degrees. All right, there we go. We've got ourselves a sketch of those two trig functions, but once I know how to sketch those two, I can sketch the other two, and now I should know what the graph of all 4 of my trig functions look like. Let's grab our calculator, though, and let's sketch each of these just to verify that the graphs are correct. I should go back to this one, and we'll put in the sketch of the cosecant function into this sketch. So go ahead and grab your calculator. All right, so go ahead and grab your calculator and put in, let's start with cosecant here. That was example 1, but let's graph 1 over the sine of theta, or sine of x. For our window, let's change that to the same window we were working with there. We went from 0 to 720. And I guess a scale of 90 should be fine there. And then for our y's, we went from -5 to 5 there in our sketch that we were looking at. So let's do that same thing here. Go ahead and graph that. There we go. That looks like the graph of cosecant that we just came up with. In fact, let's grab a picture of that. And we'll paste it into our sketch here. That, in fact, looks very close to the graph that we have. All right, let's do the same thing for cotangent. So you go to your y equals menu, and I'm going to go ahead and graph this as cosine over sine, since that's the actual way we're doing this, but you could obviously graph 1 over tangent would do the same thing for you. Oops. All right, so cosine divided by sine, and we did this on the same window actually, so we'll just graph that one and see what we come up with, and there we go. There's our sketch of cotangent. Looks very nice. Let's grab a picture of that, and we'll put it in this slide. Very good. All right, that's the end of this section 6-3.